Okay, let's look at a LaGrange multiplier method. You can say LaGrange or LaGrange, I'll probably say both. And this is one of the problems that you'll see written up in your lecture notes. And it actually covers a problem that we did a different way with the second derivative test. But I think it's important to see how the LaGrange multiplier method works. And basically, before I actually state the problem, it just means that from the two functions that we get in the actual setup, their gradients must be parallel. For instance, here lambda is a real number, and so we know vectors are parallel when one can be written as a scalar multiple of the other. So let's phrase this problem in terms of a Lagrange multiplier. So it says compute the minimum distance from the curve y equal x squared to the point 0.06. So in essence, we need to just find Euclidean distance, which we're good at doing. And because we're lazy, we're going to work with the square of the distance. So we can define a function which gives us the square of the Euclidean distance. So we'll say xy is the actual critical point. And so we'll say x minus 0 quantity squared plus y minus 6 quantity squared to give us a very simple quadratic function in x and y. So now what we want to do is minimize this distance function relative to the constraint curve. The constraint curve in your text is always written as g of xy equals some constant. So all we have to do is just put all the x's and y's, the variables, on one side, and we get our constraint curve. Now again, the simple part is taking gradients. It's very simple to take the gradient of f and g, which we can easily see here, 2x and then 2 times y minus x, and then for g, 2x and negative 1. Now, in order to write this system, we simply take each of the coordinates and write an equation. So for instance, 2x will be lambda times 2x, and 2 times the quantity y minus 6 will be lambda times negative 1. So there's your system right there. This is the system, but this is fleshed out. Now when we look at this, we're thinking, okay, we don't want to write nonsense when we move forward. And since we have x's on both sides of the first equation, it basically means we need to look at two cases. So first, let's look at the case where x equals 0. Now remember, not all problems will be this way, but this one is. And so when x is equal to 0, from the constraint curve, we automatically get y is equal to 0. Okay, so that's a possible critical number that can give us maybe something what we're looking for. Okay, when we substitute those two values into the function, of course we get a 36, very simple, and the square root of that, of course, is just 6. So that's what we got for case 1. Let's see if case 2 is an improvement on that. Remember, these are necessary conditions. For case 2, we assume that x is not equal to 0, and so now when you look up here, the 2x is just absorbed, and we just get lambda equal to 1. Now, of course, when lambda is equal to 1, we substitute here, we can easily solve for y. We'll get y is equal to negative 1/2 plus 12, and that'll give us 11 over 2. Okay, so we're thinking we got the y value, we need the x value. So let's go back to the constraint curve. We'll just set x squared equal to y is 11 over 2. Square root property, we have x is plus or minus the square root of 11 over 2. And of course now in the Euclidean distance formula, the plus or minus won't matter. We have two bona fide critical points. And when we substitute, of course, when we square this, the radical goes away. And then if we subtract 6 from 11/2 and square it, we get 1/4. And with a common denominator, we get 23 over 4. Now when we compare the two, 23 over 4 is indeed less than 6. So case 2 will actually give us the distance we're looking for. So now we see we have a minimum distance, which will be the square root of this quantity, which will give us the square root of 23 over 2. And we are done.